Hi everyone, welcome back to my channel Mastering Anesthesia, where we will discuss about difficult topics and make it easy to understand and easy to remember. In today's video, we are going to talk about one of the most commonly used IV anesthetic agent, sodium thiopental. Before we actually talk about sodium thiopental, we have to first understand where it comes from, what it is, and how they come about. Now, sodium thiopentals are from barbiturates. The parent compound is oxybarbiturate, or the fancier name would be 2,4,6-trioxohexahydropyrimidine. Don't worry, we will go into that. All barbiturates are derived from the condensation of urea and malonic acid. Now, no choice, but we have to learn how to draw the chemical structure. So for urea, it is a carbon atom with double bond O with amide group here, NH2 and NH2 gives us urea, and malonic acid is the other half of the ring. You have HOC, sorry, HOC double bond OCH2 C double bond O, and yeah, H here. So the condensation of urea and malonic acid will essentially give us barbituric acid plus water. So barbituric acid is just a combination of both of these. So it will be NH, C, O, NH, C, double bond O, CH2, C, double bond O, and NH. And we have ourselves a barbituric acid and water. Okay. So if we want to count the structure, it starts with N over here being number 1, number 2, number 3, number 4, and number 5. The 2,4,6-trioxohexahydropyrimidine name comes from pyrimidine, meaning that it is this 6-membered ring structure with nitrogen atom at the first and third chain, and then hexahydropyrimidine, meaning that this pyrimidine chain is hydrogenated and they are fully saturated, no double bonds in between this. And 2,4,6 trioxo essentially means at the position C2, C4, and C6 has this oxygen attached to it by double bond. So there you go, you have 2,4,6 trioxohexahydropyrimidine, easily explained. Now, let's talk about solubility. Oxybarbiturate, like how we discussed, are not easily soluble. Barbiturates are not readily soluble in water at neutral pH. So therefore, if we remember our ideal anesthetic agent, they are water soluble. So in order for us to impart our substance to be more water soluble, there have to be some tweaks in the structure that we have to do in order to make them more soluble. So if we look at the structure that we've drawn just now, we can change our oxygen here and change it to sulfur. This automatically make our structure thiobarbiturate, which is where we want to go in our video. Therefore, thiobarbiturate are very lipid soluble, they are highly protein bound, and they are almost completely metabolized in the liver. Whereas the parent compound that we just drew, the oxybarbiturate, they are less lipid soluble, they are less protein bound, and some are even excreted unchanged, which is unfavorable in our use of anesthetic agent. So let's actually draw sodium thiopental. Sodium thiopental has you remember the structure of the ring, you have NH, you have C, you have NH, sorry, NH, You have C, you have C here, you have another C and connected here. And double bond O, double bond S, double bond O. And here you have two separate groups. You have C2H5. Here you have CH, C3H7, and another side group of CH3. The name of this group is 5-ethyl 5-methyl butyl thiobarbiturate, or something that is more formal. Here is the drawing. You have the N carbon, N carbon, 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 where the 5, carbon number 5 has this ethyl 5-methyl butyl thiobarbituric acid. Okay, so apart from the sulfur giving it solubility, there is something else that we need to know. When we constitute barbituric or thiobarbiturate, we will constitute it into an alkaline environment. So this alkaline environment favors the tautomerism of the sodium thiopental from its keto to enol. Let me show you. The alkaline solution will favor the tautomerism of keto to enol form. This is a form of tautomerism. If you remember, tautomerism is dynamic isomerism, where a chemical structure will change its will change its properties, yeah, in different according to the environment that the substance is in. Now let's talk about sodium thiopental presentation. They are presented in a rubber-topped glass vial. It is formulated as sodium salt. In it has pale yellow powder containing sodium carbonate 6% by weight and nitrogen gas 0.8 bar. Now, why the need for sodium carbonate? Now, this is particularly important because sodium carbonate, when we constitute it with water, will give us sodium bicarbonate plus sodium ion plus OH. So this sodium bicarbonate and this hydroxide ion will confer the alkalinity of the solution at an astounding pH of 10.6. Now remember that pKa of sodium thiopental is 7.6, meaning that at physiological pH of pH 7.4, considering that our sodium thiopental is weakly acidic, if we remember our dissociation curve, here is the pKa of 7.6. Then when it gets more acidic towards this side, which is 7.4, it gets less unionized. Yeah, from pH of 10.6, when it's injected into the circulation, it goes this way towards the left, where the molecules are getting less ionized. So when they are less ionized, they are more lipid soluble, rendering it more soluble, able to penetrate the blood-brain barrier and exert its effect. And the nitrogen gas is also important in this respect because it prevents, if we use air, there's carbon dioxide in it, which can react with water to cause it to become more acidic and reduce the pH of the solution to be less, so resulting in less unionization of the solution or compound. So when we constitute it, it will leave us with a 2.5% solution, alkaline, and it is unstable once it is constituted. So it is recommended for us to use it between 24 to 48 hours after reconstituted. And it is also bacteriostatic, meaning within this recommended amount of time, you can be assured that there won't be any growth of bacteria due to this insanely alkaline solution. Next, what are some of the uses of sodium thiopental? Well, in our case, we always use it for general anesthesia, and in my practice, we always use it for obstetric anesthesia. We can also use it for refractory status epilepticus. Now, this is also important, refractory status epilepticus, because sodium thiopental has this special characteristic where it can cause burst suppression in EEG, burst suppression of EEG, and also isoelectric EEG. Yeah, so when that happens, it shows maximal CNS depression, meaning that that is the least amount of CMRO2, the cerebral metabolic rate of oxygen consumption in the brain. So it can be achieved with the use of sodium thiopental. Other than that, can also be used for sedative and also cerebral protection.